Let's now talk about some real-life applications of how we apply physics to turning corners, particularly when we're driving a car. You've probably seen some of these strategies applied if you're a fan of watching race car driving, and you might have instinctually done some of these things if you're currently on your learners or approaching your Ps. What strategies do drivers put in place in order to turn corners safely? Well, hopefully you recognise that it's a good idea to slow down. We're going to talk about why slowing down is so important here in a moment. But slowing down is a major thing. You might see, I know whenever I drive in the mountains, and it's certainly in other areas as well, if you're in really windy areas, you'll see these speed limit signs. These have been calculated using the physics that we're going to be talking about now. So slowing down is a major thing. Why is slowing down so helpful? Well, when we're actually turning a corner, we're relying on the friction of the road to keep us going in a circle. The friction is the centripetal force here. It's not the normal force. We don't have a string pulling us towards the centre. We don't have anything else like that. It's actually friction. It's a force due to friction that's pushing it towards the centre. So if we think about this, if we do sum of the forces equals mv squared over r, so we're just considering horizontal stuff here, then only force acting is going to be that force due to friction. So that's going to depend on the mass of the vehicle, the velocity of the vehicle squared, and the radius of the circle. So we can see that slowing down is going to have a huge impact on the amount of required friction. So if we handle this as the required friction amount, reducing the velocity is going to have a very big impact on the required friction. So reducing the velocity will definitely reduce the amount of friction that's needed. Also, if you have a less massive vehicle, that's going to mean that you don't need as much friction to get around the corner. Now, I'm talking about required friction here. There's only a certain amount of friction that the road can apply to your tyres. And if you go too quick, you're not going to be able to have the required friction to be able to keep going in a circle. You probably know that if you've ever been on a slippery road, you need to slow down even more because the water on the road reduces that amount of friction, therefore reduces your ability to turn in a circle. Now, we can also increase the radius here. So let's do a comparison quickly. So you'll see on your diagrams there's a geometric line of this corner here. And that's really just a portion of a circle. So this circle would have a turning radius here. But you'll see that race car drivers, they don't follow the geometric line. They're going to cut into the corner like this. And there's a very good physics reason why. So cutting into the corner like this effectively increases the radius of the circle, or at least the portion of the circle that the car is travelling in here. And increasing the radius of this circle reduces the amount of required friction, which is very, very helpful. Okay, let's have a go at an example. We've got an engineer's put a maximum speed limit sign on a dangerous bend. If the car travels too fast, the sideways frictional force will not be large enough to keep it on the road. That's why it's especially important to slow down in wet conditions on the road. So please be really careful when you're driving, everyone. In this example, the maximum sideways frictional force that the tyre road combination can produce without slipping is estimated to be blah. So that's the required friction. And we're told the mass of the car here. The bend is modelled on the arc of a circle of a radius 90 metres. So like I so precisely drew before, this is a portion of a circle. I'm not doing it again. It took ages to line those up. So that's the radius. We want to calculate the maximum speed the car can have and remain on the road without slipping. So we're in a situation where sum of the forces equals, you could write ma, but because we're in a circle, it's mv squared over r, because the acceleration is v squared over r in circular context. The only force acting is friction, and it's still going to be mv squared over r. Let's rearrange this so we can get this in terms of the velocity here. So I'm not going to substitute things in yet. I think I'd prefer to do this algebraically. So the force due to friction times r is going to be equal to mv squared. I'm going to divide both sides by m. Maybe I'll rewrite it this way first. You don't need to do as many lines of working out, but if you find it useful, please really consider doing so. So the velocity is going to be the force due to friction times r divided by m, and we're going to take the square root. Now you might remember we've talked previously in physics, if you're taking a square root you need to consider whether you're taking the positive or the negative. Because we're just talking about a speed here, we're going to be taking the positive square root. Let's now substitute. So that's about 14.49 blah 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 meters per second, not rounding. I have trouble imagining that, at least when I'm talking about cars. So let's put that maybe in kilometres an hour just to get more of a sense of what that would be like. Okay, so this one has a maximum speed of 52 point blah blah blah. We need to round this to 3 sig figs, nice, so 52.2. Let's pretend the question asked us to find it in kilometres an hour. So perhaps to be conservative, because I've never seen a speed limit sign that said 52.2, perhaps the engineer would write a maximum of 50 kilometres an hour. That doesn't mean that you look at those signs and think, oh, the engineer's rounded it. Please follow those signs. Now, I just wanted to mention this context of non-uniform motion of circles, and that basically means when we're changing our speed in a circle. I haven't seen this context in a very long time on a VCE exam, but I still think it's really worth mentioning in case, because it's absolutely within the realms of the course to be able to ask you a question like this. So in this example, we've got a car travelling at increasing speed around a circular section of horizontal road with a radius of 50 metres. The car is at P, so we've got a location here. Oh, and they've given us a compass flower, nice. So we're going to, well, I don't know why, because then they've then given us these arrows here, whatever. We're told that it's travelling south with a speed of 10 metres per second. The speed is increasing at a rate of 2 metres per second squared. Okay, so which arrow best indicates the directions of the car's total acceleration the instant the car is at P? Normally, with a uniform circular motion example, we say that the force is acting towards the centre of the circle, so the acceleration is acting in the same way. Newton's second law tells us acceleration and the net force act in the same direction. However, this is not the only force acting in this context. We must also have a driving force that's acting in this direction, because it's accelerating. Sorry, it's always accelerating if it's travelling in a circle, but it's speeding up. So there must be some driving force causing it to speed up. Now, this must mean that the net force is no longer going to be towards the centre. The net force is going to be pointing at a slight angle. So we always add our forces tip to tail. So that means we're going to have the net force will be pointing off at an angle. Now we're provided with this key here. So I guess if we had to choose one, we can't choose A, because that would be if we didn't have an increasing speed, we didn't have a driving force increasing that speed. And G would be ignoring the force that's pointing towards the centre of the circle. So I guess our best option here is H. Okay, now it says, what is the magnitude of the component of the car's acceleration in the westerly direction the instant the car is at P? Ah, this is why they've given us a compass flower. South, east, west. So the westerly component of the acceleration is the centripetal acceleration. It's the acceleration coming about due to this thing travelling in a circle. So to do that, the centripetal acceleration is A, and that's V squared over R. We're told the velocity at this instant. So this centripetal acceleration will be changing, but we are asked about this instant. And at this instant is travelling at 10 metres per second. We also need to know the radius. I should have looked that up before. Radius was 50 metres. Oh, nice. 2.0 metres per second squared. Now this one is a little trickier. It says, what is the magnitude of the acceleration of the car the instant the car is at P? We previously calculated in the last question that there is an acceleration of 2.0 metres per second squared acting towards the centre of the circle. However, we're also told that there is an acceleration due to this driving force that's acting at 2 metres per second squared. So that means we've also got an acceleration pointing in this direction due to that driving force. So you might recall the way that we add together vectors. We've got to draw them tip to tail. So 2.0 metres per second squared. And you might draw this one first off next time. and 2.0 meters per second squared. So the way to find the net acceleration is adding together these two vectors. So this vector here, let's write a total. That's got to be equal to, this is a bit of Pythagoras, 2.0 squared plus 2.0 squared, taking the square root of that. A squared total would be 2 squared plus 2 squared, so to find a total, we need to do the square root of this. We've done a little bit of Pythag. Cute. So in total, that's going to be 2.8 meters per second squared.